Dear learners, welcome back. Welcome back to our series of lectures on ionic equilibrium. I'm sure that you would have enjoyed my first session, which basically was about electrolytes and non-electrolytes and Otway dilution law. In today's session, that is part 2 of ionic equilibrium, I'm going to take up the theories of acids and bases. Basically, it's kind of a review of these theories. I'm sure that you learned about these theories in your school. But as a part of this curriculum, we need to review them so that we can go ahead and learn more about ionic equilibrium. Okay, now the session for today is planned as follows. That is, to begin with, basically we will try to talk about the simplest theory of acids and bases, that is the Arrhenius theory. Then, having talked about what is the theory, we will just briefly talk about what are the limitations of the Arrhenius theory. That's how the concept of acids and bases has grown. This is the first theory which came up there. There were certain limitations. To get over these limitations, a new theory was proposed. That happened to be the Bronsted and Lowry theory, which we'll be discussing. Then there again, there were certain kind of limitations. We will talk about those limitations there. And then we'll come down to the third theory for today. That happens to be the Lewis theory of acids and bases. And then we will try to sum up what we do in today's session. Okay, now let's start with what is the Arrhenius theory. I'm sure that you all know it, but let's try to have a relook at it. Basically, Arrhenius theory, as I mentioned earlier, is one of the first theories proposed for acids and bases. And Arrhenius actually proposed this theory way back in 1884, and this theory was proposed in the context of electrical properties of solutions of electrolytes. Basically, what happened was that Arrhenius was kind of dealing with kind of the study of electrical properties of solutions of different kind of electrolytes, and acids and bases happen to be the predominant ones over there. And in this context, that means when he was trying to explain that what makes these electrolytes conducting, he proposed that the electrolytes, when you put into water, say I take sodium chloride, put into water, it dissolves and starts conducting. That means the solution of sodium chloride happens to be a conducting one, which we discussed in the last session also. Now, this is his proposal. That's the way he proposed the so-called the theory of electrical conductivity in a way. And prior to Arrhenius, the earlier belief was that it is the passage of current through the solutions that generates ions. So we have to understand the importance of this theory here. Basically, prior to Arrhenius, people thought that you have a solution there, and when you pass electricity through that, then only the ions are generated and they start conducting there. As against that understanding, Arrhenius said, no, we don't need to pass electricity for it to get conducting. The electrolyte itself has ions. When you put into solution and you make a solution from there, then these ions get dissociated, and these ions are then able to conduct electricity. So that is the so-called theory, Arrhenius theory of electrolytic conduction. And that means important thing here was that the passage of electrical current was not necessary for the system to be conducting. So ions are already there. The system, when the electrolyte dissolves in water, makes a solution, there are ions there, and they are the ones which conduct electricity. That was a generic kind of a theory proposed by Arrhenius. That was true of all electrolytes. Acids and bases happen to, as I mentioned earlier also, the predominant ones over there. Now, in the context of acids and bases, what he said was that an acid can be defined as a substance that produces hydrogen ions by dissociating in aqueous solution. That means if I take HCl, put into water, that will dissociate to give me hydrogen ions and chloride ions there. So it is producing hydrogen ions, so it is acid. If I take citric acid, if I take acetic acid, for that matter any acid I take, even if I take a carboxylic acid there, say benzoic acid, though it doesn't dissolve very well, but if I take any acid which dissolves in water, say formic acid, acetic acid, citric acid, there are different examples over there. So they all produce hydrogen ions. So any electrolyte which produces hydrogen ions in aqueous solution is said to be an acid. That is the way Arrhenius defined acids there. So if I take the example of a generic an acid HA, that's a typical way of representing an acid there. So that acid will dissociate. This arrow indicates a dissociation of that to give you hydrogen ions and A minus there. So A minus happens to be the anion of the acid there. Now, as per this definition, what we see is that all acids, irrespective of what acid you take, they all produce hydrogen ions there. Since they all produce hydrogen ions, they have similar properties. I'm sure that in your earlier classes, say class 6th, 7th, you learned about acids to be having sour taste and things like that. So all those properties are there because all the acids produce hydrogen ions over there. Okay. So what about the bases there? So before we come to bases, one more thing we have to understand here, that we just said that Arrhenius said anything which produces hydrogen ions is an acid. Fair enough. But can a hydrogen ion exist in water? That's a very important question there, because if you know what is hydrogen ion is an hydrogen atom from which we have removed one electron. So basically it is just a tiny nucleus there. There's only one proton, and this proton is very, very small in size. Since such a small nucleus of hydrogen atom in a way and has one full unit of positive charge, so that means the charge density is very large. So if you have a particle having such a high charge density and you are putting it into a medium, which is water in this case, and that happens to be polar. So what happens is that this proton which is there in the system, that cannot exist as such, that will combine with water molecule to give what's called as a hydronium ion. We represent it as H3O plus, and that is how we can represent it there. That is H plus, that is the hydrogen ions produced in aqueous medium that combine with water molecule and to give you a hydronium ion there. And structurally we can represent like this. This is the proton, and then this is shown by different color. There's a water molecule there, and this positive charge which was there on this proton is actually on the overall molecule, that is H2O plus. So that is the way we look at the hydronium ion, which is a very common term. I'm sure that you all know about it. But more recently, it has been found that the charge density on proton is so very high that it's not that only one water molecule combines here. Rather, the proton exists something like this. It means you have a proton that combines with the water molecule to give you hydronium ion, and even this hydronium ion has certain polarity there. And so this kind of structure, that means there are three water molecules, one here, one here, one here. They all combine together to make a large molecule, a large ion, not a molecule, having a formula H9O4 plus. So that is the way, because this has been established as kind of spectroscopically. That means this species does exist in aqueous solutions. Okay, but for all practical purposes, we use H3O plus as the way proton exists in water. Okay, let's move ahead. And if I see the ionization of HCl in water, how do we represent that? Basically, we can tell it that there's a HCl solution there. If you take HCl, put it into water, that becomes aquated, and then you react with water to give you this proton will be lost there. That will be taken by this water molecule. So that means this proton is generated there, and this water molecule kind of solvates it or hydrates it. So give you a hydronium ion there, and you have a chloride ion over here. Okay, so according to this equation there, we can even use Arrhenius theory to define an acid to be a substance that when dissolved in water produces hydronium ions, because that is the way it exists there. Though initial definition what Arrhenius gave was that anything which gives you proton is an acid, fair enough. But now we know that proton cannot exist as such, it exists as hydronium ion. So we can say that an acid may be defined as a substance which when dissolved in water gives you a hydronium ion there. Okay. Now if I look at ionization of acetic acid in water, so what you find is, this is acetic acid, I'm sure you all know that. When you put into water, what you get is hydronium ions, and then you get a acetate ions there. So what you see the difference here and in this equation there. Here we showed a single arrow indicating that the reaction goes far to the right. That means as a kind of a complete dissociation of HCl. Whereas in this case, there is ionization of acetic acid and there's an equilibrium there. That means the reaction doesn't go far to the right. There's an equilibrium between the right and the left part of it. That means this does not go completely in the right direction. That means the acetic acid ionizes to only a certain extent there. Thereby, we say this is a weak acid there. So a strong acid will be one which dissociates completely to give you hydrogen ion and the counter ion over there. Hydrogen ion, or you can say hydronium ion there. Whereas a weak acid will be the one which will dissociate, or rather not dissociation, it's ionization, which will ionize to certain extent to give a situation, a system wherein there is an equilibrium between the acid and the corresponding anion over there. Okay, continuing further, if you look at the base now, let's take a look at the example of sodium hydroxide. If I take sodium hydroxide, put it into water, what do I get? I get sodium ions and hydroxide ions over there. So it's very straightforward. That means this is a base, and that's the way Arrhenius defined a base to be. A base is a substance that produces a hydroxide ion on dissociation in aqueous solutions. Fair enough. Now, similar to what we had in case of acids, let's look at the ionization of ammonium hydroxide in water. What you find is ammonium hydroxide, when you put into water, that gives you ammonium ions and OH there. That means this is again an equilibrium situation which suggests that our ammonium hydroxide happens to be a weak base there. Okay, so what you have seen is that according to Arrhenius theory, anything which gives you a proton or a hydronium ion is an acid. Anything which gives you an OH ion is a base. If it goes completely right direction, that means there's a complete association, it's a strong base. If there's an equilibrium situation coming there, there's a partial ionization over there, then we say it is a weak base there. Okay, now if I look at the reaction between, say, HCl and NaOH, we know that HCl is a strong acid, NaOH is a strong base. When the two react together, what will happen? If I take, say, I take a beaker containing certain amount of water there, and to this I add certain amount of HCl and also NaOH. What will happen? HCl will dissociate to give me hydrogen ions and Cl ions there, whereas NaOH will dissociate to give me sodium ions and OH ions there. So that will be that means the solution will contain 4 different ions over there. Now if you go further, what you find is that these 4 ions have written again over here, and this hydrogen ion and OH ion, hydrogen and OH ion, they can combine to give me a water molecule over there. And if I look at this equation, in this equation I have got 4 ions on this side, H plus, Cl minus, Na plus, OH minus, and on this side Na plus, Cl minus and H2O. So if I cancel these ions there, NaCl, Na plus and Cl minus here, Na plus and Cl minus here, if I cancel the two together, what do I get is, I get a simple reaction there, that is H plus aqueous plus OH minus aqueous, giving me water molecule there. That means essentially the neutralization of a strong acid and strong base primarily is a reaction between a proton and hydroxide ions over there to give me a water molecule there. Now in such a scenario, if I look at what is the role of sodium ion and chloride ion, they play no role in this neutralization reaction there, and that's why they are called as spectator ions there. That means the sodium ion and chloride ions which do not participate in the neutralization reaction, they are called as spectator ions there. They are just there. They do not do any, they do not participate in the process of so-called neutralization of acid and base. So neutralization of acid and base primarily is a reaction between a proton and a hydroxide ion there to give me water molecule. Okay, I'm sure that you will keep this in mind. Okay, let's move ahead. Let's move ahead and see that this is a very simplistic theory over there. However, it has got certain limitations, and the limitation happen to be as follows. That is, firstly, that is, it is applicable only to aqueous solutions, because we know that right from the beginning we have been saying that anything is an acid which, when dissolved in water, gives me a proton or gives me OH ion if it's a base. Okay, so there is a necessity of water to be a system, a part of the system there. That means this theory is applicable only for aqueous solutions. However, this also doesn't explain that these are limitations now. This is the first limitation, that is applicable only to aqueous solutions. And other limitations are that it doesn't explain the acidic behavior of some substances that lack hydrogen. Because we know that aluminum chloride is an acid. Sulfur trioxide we know is an acidic oxide. N2O5 is an acetic anhydride. We know that all these things are acidic in nature. But the acidity of these kind of systems is not explained by Arrhenius theory. Similarly, you can look at, we know all fairly well that ammonia is basic, but it doesn't have any OH there. So how do we explain that? How do we explain the basicity of ammonia or sodium oxide or maybe even sodium carbonate? So these are certain limitations of Arrhenius theory, and that leads us to the new theory, the theory which came thereafter, and that is called as Bronsted and Lowry theory. Bronsted and Lowry actually worked on one of the limitations of Arrhenius theory. That means, and that happens to be that because the very first limitation we pointed out about Arrhenius theory was that it is applicable for aqueous solutions only. So Lowry and Bronsted went slightly ahead and they proposed a theory which doesn't need the participation of water molecule as such. Though it is applicable in case of water as well, but it is not necessary to have water to define an acid or a base over there. Let's see what is the theory here. According to Bronsted and Lowry, an acid is defined as a species that can donate or transfer a proton to another species. So here again we need proton. That means, but we're not saying it to put into water. That means there are two species. One is able to donate a proton. The one which can donate a proton is an acid, and the one which can take a proton, accepts that proton, becomes a base. So that is a very slightly broader way of looking at acids and bases rather than what we had in case of Arrhenius, wherein we had to put system into the aqueous medium there. Okay. Now, so in such a scenario, that means when acid is the one which can donate a proton, base is the one which can accept that proton. So the acid-base reaction basically becomes a proton transfer reaction. That means it's very, very straightforward. That means a species is transferring its proton to another species there. Let's look at this example here. So you see there is ammonia and there is HF, hydrogen fluoride acid, hydrofluoric acid. Now what happens is, so in this case, if you look at this reaction, what's basically happening? This proton from HF is going to ammonia and is becoming ammonium ion there and this is fluoride ion over there. So here this is an acid. HF is acting as an acid because it is donating a proton. Ammonia is acting as a base because it is accepting that proton. So HF is an acid, ammonia is a base. Very straightforward there. So what we see is that in this particular way of looking at things, in this definition here, there is no requirement of water. Because it can happen, if you just take even ammonia as a gas, HF as a gas, the reaction can take place. Okay, so there is no need of water as a solvent there. So, however, if you still go further, we find that in this case, it involves transfer of protons. It is applicable to protonic solvents only. So that is that's another kind of a limitation, but it is slightly broader than what Arrhenius proposed earlier. Okay, let's move ahead and see that is this theory applicable for aqueous solutions also? The answer is yes, and let's take an example for that. Example for that again is I'm taking ammonia, I'm taking HF. If mind you, I'm taking ammonia, I'm putting aqueous here. That means basically I put into water because it is in water medium, aqueous medium there. HF also is an aqueous medium, and then of course you have water as a solvent there. So if this reaction takes place, what do I get is, so this ammonia, HF and water, when they react together, ammonia stays, just to simplify it, we're putting it like this, that ammonia stays as such, and then these two react together. That means HF gives a proton which is taken up by water molecule, so that becomes hydronium ion there, this becomes F minus there. That is the first step, just to make it things easy to understand there. I put this same thing again over here, NH3, H3O plus and F minus. Then what we see is that these two react now. And what happens is this hydronium ion gives a proton which is taken up by ammonia there. So it becomes ammonium ion there, and this becomes water back. And then of course the fluoride ions stay as they are. Now if I cancel fluoride ion from both sides, what do I get? I get ammonia plus hydronium ion giving me ammonium ion and water there. So what does it mean? If I start from here and we reach somewhere here, so what do I find is the role of water basically is to take up a proton from HF and hand it over to ammonia there. Okay, so that means the water is playing the role of a mediator in the transfer of proton from HF to ammonia. We have seen in the previous slide here, that is the reaction between HF and ammonia is just that HF is donating a proton as acting as an acid, ammonia is accepting that proton acting as a base. So they were doing it between themselves. Now in aqueous medium, water is doing that job of taking proton from HF and handing it over to ammonia. So that is the way reaction happens in aqueous medium there. Okay, let's move ahead. And this is again a very, very important observation vis-a-vis the Bronsted and Lowry theory, is that if you write an acid-base equilibrium, let's take an example here again, because the example we just discussed here, that is ammonia in aqueous medium. So if I put it into water, so what do I get is I get ammonium ion and a OH minus there. So here this is acting as an acid, this is a base there, and if you look at the reverse direction, this is an equilibrium here, mind you, and if you look at the forward direction, so this is acid, this is base. In the backward direction, ammonium ions are acting as acids because they are donating a proton which is picked up by hydroxide ions there. So in acid-base equilibrium, both the forward and the reverse reactions, they involve proton transfers. So this is a transfer of proton from water to ammonia. Here this is a transfer of proton from ammonium ion to OH minus. But the question now comes up is that in actual system, suppose I take ammonia, put into water, where would the equilibrium be? So the actual direction of the equilibrium will depend on the relative strengths of acids and bases. Let's understand that. But before that, let's understand one more thing, which I just mentioned earlier too. That is, this is a base here. We know that ammonia is a base. And since water is donating a proton, it's acting as an acid there. Ammonium ions, we just mentioned, it's an acid because it's giving a proton to OH minus. This happens to be a base there. Fine. What you see is that in this case, there are species which are interrelated. You see that this is a base. It takes up a proton and becomes an acid there. So that ammonium ions and ammonia, they are related. They are related as conjugate acid-base pair. So this is an acid, ammonium ion is an acid, whereas ammonia is a conjugate base of ammonium ion. Similarly, water is an acid and OH ion is a conjugate base of this acid there. That's one part of it. Secondly, as you have seen it here, when you represent the acid-base equilibrium according to Lowry and Bronsted theory, what we basically do is that the conjugate acid-base pairs, they are designated by the same numerical subscript. That means ammonia and ammonia and ammonium ions, they are related, so they are given the same subscript there, 1, 1. This water and OH ions are related, so this is 2, 2. So that means they are designated by the same numerical subscript over there. That's very important here. Okay, now let's go ahead and see that where would the equilibrium be. That equilibrium in such a situation will depend on the relative strengths of the acids and bases involved in the reaction. Let's understand what do I mean by that. Now if I look at this case, say HF plus water giving me hydronium ions and F minus, that is a fluoride ion there. So as you can see it here, HF is an acid, it has given a proton to water, this becomes a base, and that gives me a hydronium ion that actually becomes an acid now, because this is coming as a consequence of acceptance of proton by water molecule. So So you can see that water and hydronium ion, they are related. So this is acting as a base. So this is a corresponding conjugate acid there. So you can see since the two are related, so this is base 2, this is acid 2. Similarly, HF is an acid. Since it is given a proton, so what do I get as a consequence of this losing a proton is I get a fluoride ion there. So that's a base. So this base and this acid are related to each other. Okay, so that is the meaning of conjugate acid-base pair. That means any acid will have a corresponding conjugate base and vice versa. Now, I erase my question again. My question was that in such a situation, where would the equilibrium be? That we can decide by looking at the relative strengths. In this case particularly, what we see is, so let's start from here. This HF is an acid which is going to lose a proton. It has a tendency to lose the proton. Now in the system, there are two species which have a tendency to accept a proton. One happens to be water molecule, one happens to be fluoride ion there. Both have a tendency to accept proton. So both of them are bases in the system. And now what we find is, that means this proton which is given by HF can be taken up by water or by fluoride ion. But what is experimentally found is that this equilibrium lies towards the left hand side. That means the fluoride ion, that is this one, is a stronger base than water. Okay, so that's why the equilibrium lies to the left. Had water been a stronger base, then the equilibrium would have gone to the right hand side there. Okay, so that is how do we determine that where would the equilibrium be, or the other way around. So if I know that equilibrium is toward the left side, so we interpret that fact in terms of fluoride ion being a stronger base there. Let's take one more example here. Say the example wherein we just take HCl, put into water, and we see that we have put a single arrow indicating direction goes far to the right. Okay, so here HCl is an acid which is going to lose a proton, and here again, as before, I've got two possibilities of bases. One happens to be water which can take a proton, or we can have a chloride ion which can take that proton. Since the reaction goes far to the right, what does it mean? This means that the chloride ions is a weaker base than water. Had it been stronger, reaction would have gone like this. That means H2O is a very, very strong base as compared to chloride ion there. Okay, that's why the reaction is going in the forward direction, because since it is a strong base, it will take proton from HCl and go in the forward direction. Okay, so from these two examples, what do we infer? What do we infer is the following, that in a conjugate acid-base pair, a weaker acid has a stronger conjugate base, whereas a stronger acid has a weaker conjugate base. Let's see it here. So this is a strong acid, its conjugate base is very, very weak. Okay, this is a weak acid, its conjugate acid is a stronger one over there, or you can say the other way around. This is a acid, its conjugate base is this one. Okay, so essentially in an acid base conjugate pair, or you can say conjugate acid base pair, if the acid happens to be stronger, the corresponding base will be, the conjugate base will be weaker, and if acid happens to be weak, the conjugate base will be stronger. Okay, so that is a very, very important aspect of this Brauerian Laurie and Bronsted theory about acids and bases. Okay, let's go ahead and again look at this thing, that according to this theory, since we are talking about transfer of proton, that means if I want to look at this, for a system to be acidic in nature, it must have at least one ionizable proton. Then only it can be an acid, then only it can transfer the proton there. Similarly, a base should have a possibility of accepting that proton. How does a base accept a proton? It has to have a lone pair of electrons. Say in case of ammonia we saw. In case of ammonia, there is a lone pair of electrons on nitrogen atom. That's where the proton which is given by HF comes and binds there to give me ammonium ions there. Okay, so but now question comes is, suppose you have a system, you have a molecule which has a proton which can be ionized and also has a lone pair. So what will happen now? Will it act as an acid or a base or both? Let's understand with the help of an example there. Let's take a simple case that is of water there. We know that structure of water. In water there is an oxygen atom there and there are two hydrogen atoms attached to that one. That means there are two OH bonds there, and on oxygen there are lone pairs there. So since in case of water there are lone pairs there, so water can act as a base, it can accept a proton. And since this OH in case of water, that the OH bond is ionizable, that means the proton can be lost from there, so it can act as an acid also. And let's see, what we find is that water can act as an acid as well as a base. Let's take some examples here. See, I take the reaction of, say, carbonate ions. Carbonate ions in water, basically they accept a proton from water to give me bicarbonate ion, and you generate an OH ion there. So in this reaction what we see is that water has donated a proton to carbonate ion, which has become bicarbonate now. So water is acting as an acid here. And if I take another example here, say acetic acid. In case of acetic acid, I take water again. In case of acetic acid, in this reaction we are seeing that acetic acid is losing a proton and becoming an acetate ion there. So acetic acid is acting as an acid. So water will be acting as a base here. Here water was acting as an acid. So water can act as an acid or as a base. And means that will depend on what is the other species in the system there. And such species which can act as an acid as well as a base, depending on the nature of other species in the system, they are called as amphoteric in nature. That means water is amphoteric because water can act as an acid or can act as a base depending on what is the other species in the system there. Okay, let's move ahead and see that let's try to analyze this, the Laurier-Bonston theory. It has a wider applicability vis-a-vis the Arrhenius theory, because acid does not depend on the nature of solvent there. In case of Arrhenius theory, we have to add water. Only in aqueous mediums the theory is able to tell you what is an acid, what is a base. Whereas in case of Bonston and Laurie theory, there was water can be there, but even without water also we can talk about acids and bases, as we did in case of ammonia and HF there. Ammonia is a base, HF was an acid there, because HF donated a proton, ammonia accepted one there. However, this also has limitations, because this is a strength there, because this having wider applicability as compared to Arrhenius theory is the strength of Bronsted and Laurie theory, but it still has weaknesses and the limitations, and they happen to be as follows. That is, it is applicable only for protonic systems, because systems which can have protons, if something doesn't have a proton, then it cannot act as an acid. How does that act as an acid? Because it doesn't have a proton. It cannot act as an acid according to Bronsted and Laurie theory. It can still act as an acid, we'll come to that. But the question is with respect to the Bronsted and Laurie theory. Okay. So let's look at some examples there. So we know that AlCl3, aluminum trichloride, we all know that it is an acid. It shows acidic behavior, but we see that it doesn't have a hydrogen atom. Since it doesn't have a hydrogen atom, so according to Laurie-Bonston theory, it cannot not act as an acid because it cannot donate an H plus hydrogen. Okay. Similarly, sodium carbonate, it doesn't have an OH, so it cannot act as it cannot generate OH ions in aqueous medium, so it cannot act as a base in terms of Arrhenius theory. Or this also doesn't have lone pair of electron to accept a proton. So here again, it is not acting as a base. But we know that this AlCl3 is an acid, sodium carbonate is basic in nature. That means these two experimental observations are not explained by either the Arrhenius theory or Bronsted and Laurie theory there. That means both these theories are fairly good. They are able to explain a lot of things there, but they've kind of become inadequate in these two examples over there. That means we have to have one more theory, another theory, And that theory which came up later on was what's called as Lewis theory. It is still more advanced than the first theory was Arrhenius theory. That means something which can generate a proton in aqueous medium is an acid which generates OH ions is a base, or hydronium ion or OH ions, acid and base, and so on and so forth. And then we went slightly ahead, and according to Bronsted-Lowry theory, there was a proton transfer. Something which donates a proton is an acid, which accepts a proton is a base. Okay. Now let's move further. Lewis theory, it goes beyond that, and it says, which actually came in 1923, which proposes that that means the behavior acid base. That means according to this theory, acid base behavior is not limited to systems having H plus or OH ions there. It goes beyond that, and sorry, Lewis talks about acids and bases in terms of lone pair of electrons. And an acid is, according to Lewis theory, an acid is a species that forms a covalent bond by accepting a electron pair from another species. So now we started with generating OH ions and hydrogen ions there. Then we came down to transfer of a proton. Now we're coming down to a system which can give an electron pair or accept an electron pair. So anything which can accept an electron pair is an acid, and the one which can donate an electron pair is a base. So it's an even broader kind of a definition of acids and bases there. Let's take an example to understand this. So these acids and bases, acid, something which can accept an electron pair, base which can donate an electron pair. So they are called as Lewis acid and Lewis bases. Look at this example there. So basically, Lewis acids will have vacant orbitals that can accommodate the electron pairs which can come from Lewis base. And Lewis bases will be the one which will have lone pair of electrons which can be donated or shared. Look at this example now. So what you see is, look at the example at ammonia and BF3 reaction, boron trifluoride here. So you see the structure of ammonia there. So there is a lone pair of electron on nitrogen atom there. Whereas in case of BF3, if you look at the boron, so there are 2, 4, 6. There are 6 electrons there. That means the octet is not complete over here. That means in case of BF3, boron atom is electron definition in one way. And when these two species react together, that means this ammonia donates this lone pair of electron which is accepted by BF3 and forms this kind of a system there. So this is called an adduct there. So this reaction gives you a reaction between a base and an acid there. This is a base because it's donating a proton, donating a electron pair. This is acting as an acid because it's accepting that lone pair of electron there. Let's look at one more example there. And as I just mentioned here, so the product of the base and the acid in case of Lewis theory is called as an adduct. This is another example here. We have got oxide ion there. There is SO3. There gives you SO4 2 minus there. So there is a vacancy here. So this lone pair of electron comes and accommodates over here. Similarly here also SF4 and 2 fluoride ions. So they can be accommodated here. What you get is the structure of SF6 2 minus there. Okay. So as I just mentioned, the bond between the acid and base is called dative or coordinate bond, and the species what we get as a consequence of this bond formation is called as an adduct. Okay, let's sum up what we've done today. What basically we've done is we started by defining acids and bases in terms of Arrhenius theory, and we said anything which can generate a proton or a hydronium ion in aqueous medium is an acid, which can generate OH ions is called as a base. And then thereafter we discussed the limitations of Arrhenius theory, that is limited to only aqueous medium, and then it cannot explain the acid base behavior of a lot of species there. Then we took up Bronsted-Lowry theory, which basically was something which can donate a proton and something which can accept a proton. That means this was applicable only for protonic systems there. And then this was better than the Arrhenius theory, but it again had limitations because it didn't explain the acid-base behavior of, say, aluminum chloride and sodium carbonate and things like that. Then we came down to Lewis' theory of acids and bases there. So that's where we stop for today. In the next session, we will continue from here